Okay. I hope all of you already know me. If you don't, I think we have a problem. Fun.
Yeah, and hopefully you know me too. Yes, it's great to see our shiny faces this morning.
Okay, so today we're going to talk about emergence. So we'll specifically talk about emergence in AI systems, so such as large language models. So the way we're going to do this is we're going to start by defining the concept of emergence, and then we'll walk through several examples of.
No,
Yeah.
I'm sorry to interrupt you, but I'm looking at that warning, and it's not going to play the videos. Let's fix that really quickly, and then we can.
Oh.
Yeah, I don't know why. Yeah, do that really quickly.
Yeah. Okay. Give me 1 second. I'm on it, trying to request access.
Yeah.
Oh, I think that worked. Actually, wait, I think it's because okay, I think I fixed it.
Okay, cool. Okay, and you can
It's
just
done.
maybe start that again, and we'll just edit out that first part.
Cool. Okay, so today we're going to talk about emergence. We're specifically going to talk about emergence in AI systems, such as large language models. And the way we're going to do this is we're going to start by defining the concept of emergence, and we'll walk through several examples of just naturally occurring emergent behaviors. What we're also going to do is we'll talk about signs of emergent behaviors that have been seen in large language models. And then Ron and I will both present arguments for and against abilities that are perceived as emergent in large language models. And then we want to hear from you. So after we just build an understanding of what emergence is, how it may or may not be seen in large language models, we want to know how you think. So Ron and I actually think of emergence in AI systems a little bit differently. So at the end, we'll just do an audience poll, and then we'll both also share what side of the argument that we're on. And then I think we should have a ton of time for Q&A. So why do we care if AI systems if AI systems exhibit emergent behavior? So I think that this is a question that is just at the very heart of what it means to understand intelligence. So are large language models a significant milestone in just creating truly intelligent systems, maybe even, paving the way to artificial general intelligence? Or are we just spectators to a sophisticated but ultimately superficial display of mimicry of human-like responses that are a dead end? This is also not just a technical exercise or an academic questions. So by comparing artificial intelligence to natural intelligence, we are not only learning more about AI systems, but also about ourselves. So we're learning about what makes us intelligent. Can machines, reflect or even enhance that intelligence? Then it's also that the emergence of new capabilities in AI systems encourage us to consider its ethical and societal implications. So when an AI system demonstrates behaviors that resemble creativity or reasoning, it actually challenges our perceptions of what it means to be creative or what it means to reason through really complex problems. And then we have the matter of AI safety, right? So as AI becomes a bigger part of our daily lives, recognizing emergent behaviors is really important to make sure that these systems operate within the expected bounds. Unexpected behaviors can be a source of innovation, but then at the same time, they can also pose risks if they're not properly managed. So this is about, making sure that as AI systems are starting to drive cars and manage our finances or assist us in medical diagnosis, they're doing it in a way that is just safe, it's predictable, and it's aligned with our intentions. So that was a very long-winded way of saying that AI systems exhibit emergent behavior or not. It just touches upon, I think, really fundamental aspects of our relationship with technology. It's about our quest to understand intelligence. It's about the need for safe and ethical considerations. And it's about our journey towards the future of AI. Okay, so now let's define emergence. What is emergence? So emergent properties can be defined as those properties that emerge in a complex system that are different from those of the components that make up that system. So this concept can actually be traced back to the mid-19th century. It was introduced by English philosopher John Stuart Mill in his work, A System of Logic, which was published in 1843. So Mill was actually among the first to articulate the idea that the collective properties of a system could be more than just a sum of its parts. He said that even if we had complete knowledge of the individual parts, this would not necessarily enable us to predict or understand behavior of the whole. So this idea actually challenges us to look behind the individual elements and see the system as a whole. So recognizing that it may just possess qualities that are entirely distinct from those of its components. Then in 1972, an American theoretical physicist, Philip Anderson, provided a refinement to the concept of emergence. So he stated that emergence is when quantitative changes in a system result in qualitative changes in behavior. And Anderson's definition challenges the traditional reductionist viewpoint, which is that a thorough understanding of the most basic elements of a system should, theoretically, enable us to explain all the phenomena within that system. So he counters this perspective by illustrating that at each ascending level of complexity, so this could be physics, chemistry, biology, there are entirely new properties and behaviors that emerge that are not just extension at the lower levels. So these emergent properties require their own unique explanations and then cannot be inferred solely from the laws that govern the simpler entities. So this insight actually led to a shift in how we approach the study of complex systems. So his work showed the need for interdisciplinary approach to science, with acknowledging that systems can't always be understood by drilling down to their most fundamental components. So instead, what we need to do is look at interactions between these systems that can give rise to new emergent phenomena at each level of complexity. So for example, if we look at the human brain, it's composed of approximately 100 billion neurons. But consciousness, thoughts, and emotions that it generates cannot be fully explained or predicted by examining individual neurons in isolation. So the qualitative leap from electrical and chemical activity of billions of neurons to the interplay of human thought and emotion just shows us how emergent properties can defy simple explanations, and that requires us to adopt new perspectives and methods to understand them. And then more recently, several researchers defined emergence in the context of AI systems, and specifically large language models, as an ability is emergent if it is present in larger models, but not in smaller models. So the difference between a small and a large model in AI is the number of learnable parameters. So for AI systems, a model size is typically measured by the number of parameters it contains. So a higher number of parameters will allow for more complex information processing and pattern recognition capabilities. So to kind of put that a little bit in perspective, early iterations of large language models, such as GPT-2, had about 1.5 billion parameters, which at the time was groundbreaking. GPT-3 had 175 billion parameters. And now GPT-4 and some of the recent large language models have trillions of parameters. So what kind of defines large in a language model continues to evolve. But the principle that's kind of highlighted by this definition is that as models grow in complexity, they begin to exhibit new abilities that are not observable in some of their smaller counterparts. So this isn't necessarily just a matter of scale. It's about crossing thresholds where the accumulation of quantitative changes leads to qualitative transformations in capability. So the leap from the small to the large models, it's not just about doing things faster or more accurately. It's about unlocking new potentials. It's about discovering new capabilities that we couldn't have actually anticipated based on our experiences with less complex systems. Okay, so to sum that up, emergence is a holistic, at its core, a holistic phenomenon. So a system's behavior cannot be fully grasped by dissecting it into components, but it's actually the interaction of these parts that gives rise to new properties and capabilities. Which brings us to our second point, is that it's fundamentally about the interactions within a system. So it's the dynamic interactions that lead to unexpected outcomes. So emergent properties are not just a sum of individual components, but a result of their interplay. And then a key aspect of emergence is the qualitative leap in capabilities or behaviors that occur as the system scales. So this transformation is what distinguishes emergent abilities just from like a linear progression or incremental improvement. So it's not just a qualitative increase in performance, but it's a fundamental shift in the nature of the system's output and capabilities. And then emergence is inherently tied to scale. So the properties and abilities that emerge are often dependent on the scale of the system. So what this means is that as certain behaviors or capabilities, they only become apparent or possible once a system reaches a certain threshold of complexity. And I believe I hand it now to Ron to walk us through some examples.
Thank you, Numa. Okay, so that was a lot of theory about the background of emergence, and we're going to take a look at some concrete examples. So this is, animation of some traffic flow. This is a non-biological example of emergent behavior. The idea here is that, each individual vehicle is just following its own rules. Each driver is maintaining distance from the other vehicles, obeying traffic signals, adjusting the speed. But the aggregate complex pattern that emerges has, these interesting properties. There are traffic jams. There are wave patterns or spontaneous lanes formations that will appear. And again, none of this is dictated by any single car. This is the result of the interactions of all these different individual vehicles making isolated decisions. But the emergent behavior you see, like maybe a sudden onset of a traffic jam, can arise from the collective actions of the drivers. And it's not from the properties of the individual cars or even the individual intentions of the separate drivers. And then on the next slide, we'll take a look at a biological example of emergent behavior. Okay, so this is a video, and there are thousands of starlings flocking. We've all seen this before. This is so common that it has a name. This is called a murmuration when starlings flock like this. And again, this arises from simple rules. Each bird is following just a set of really, really simple rules that collectively result in this complex coordinated pattern. And what's really interesting is there's no plan, there's no central leader. This just arises from each of them following a set of simple rules. And we know what's really cool about this is we know that it is a set of simple rules because we can simulate this amazingly accurately. So take a look at this next video. In the mid 80s, a researcher developed an artificial life program called BOIDS, which stands for bird objects. And he found he could simulate realistic flocking behavior by just having each one of these little software BOID objects follow three simple rules. One, just avoid hitting your fellow Boids, avoid collisions. Number two, try to match the heading of your nearest neighbors. Don't worry about everybody, but just given some sort of radius, a circle around you, try to match the heading of those Boids around you. And lastly, stay close to your neighbors. And if you follow these simple rules, you can see in the beginning when this video loops, everybody starts off in a chaotic, random direction, and very quickly you get organized flocking behavior. And this Boid algorithm is used pretty much extensively. If you've ever seen an animation, CGI movie in the last 30, 40 years, it is using this Boid algorithm behind the scenes to model bird flocking, schools of fish, or herds of animals. And with that, I think I'm turning it back over to you, Numa.
Yes, you are. Okay, so now we're finally at the meat of this talk. We did it. and we're going to talk about how we see emergent behaviors in large language models. Sorry, every time I go to the next slide, it mutes or unmutes me. So if it does that, let me know. Okay, but first, let's very quickly go over what a large language model is. So the large language models that we see today, so these are the models that are behind ChatGPT and other similar systems, are trained on massive amounts of uncurated data from the internet. And the way that they work, so the task that they're trained on is to predict and complete text based on patterns that are learned during the training process. So as the model size and the training data's diversity and volume increases, the model's ability to learn patterns and generate complex, coherent, and contextually relevant text improves dramatically. So today's foundational large language models aren't intended to be task specific. They can be fine-tuned for several use cases, but because of how the training phase is structured, and then the very general purpose nature of the task that they're trained on, which again, it's simply to predict what word fits best in the given context, they're able to generate text very fluidly in a variety of contexts. So this makes them ideal candidates for a broad range of tasks, but it has also given them some unexpected capabilities in tasks that they're not explicitly trained for. So this graphic illustrates that as the number of parameters in a language model increases, we reach certain critical points where new abilities suddenly appear. So these aren't just gradual improvements, but these are qualitative leaps in what the model can do, which can be indicative of emergent behaviors. So what this means is that for a specific task, we would expect a model with 100 billion parameters to achieve about like 10% higher accuracy than a model with 100 million parameters. But a model with 100 billion parameters, which are today's large language models, are now able to do tasks that a smaller model, so like 100 million parameter model, can't do in somewhat unpredictable and unexpected ways. So a lot of the early models could perform, basic text prediction. They could do very simple question answering. And then as these models started growing, we started seeing them not just answering questions, but being able to engage in really nuanced dialogue. They were able to create really compelling narratives. They were able to generate poetry and song lyrics. And one of the most striking examples of emergence is the ability of the newer and larger models to be able to solve really complex problems around just various domains, so including math and science, and the ability to generate very functional programming code. So this capability was actually just virtually absent from the smaller models, but it emerged as the model scaled. So researchers have found that a model's ability to do addition, subtraction, multiplication was actually emergent. GPT-3 actually got no answers correct until a 13 billion parameter model size. So in that same way, GPT-3 and other models were found to significantly improve their ability to answer questions about just a wide range of academic topics, including math, history, law, only about reaching 70 billion or more parameters. So as the training process and the scale of language models, as the training process and the scale of large language models are, they're just intimately tied to the concept of emergence. So as these models grow in size and are trained on just increasingly diverse and comprehensive data sets, they began to exhibit emergent behaviors. So again, these are behaviors that are, these are just capabilities that are not explicitly trained or anticipated. So this demonstrates how quantitative increases in a model size and training data can lead to qualitative transformation in its capabilities. But these emergent abilities don't actually follow the scaling law, right? So before people started building, larger and larger models, it actually used to be really well known that model size correlates with model performance on a range of common tasks. And you could predict performance improvements just based on empirically derived scaling laws. But no one could have predicted that these emergent abilities that have been seen with the large language models with the scaling laws. So it's really difficult to say with what certainty whether larger sizes could promote even, greater capabilities, or at what model size these improvements would stop, or just even how to think about these tasks compared to those where accuracy maps to model size. So right now, we don't know at what scale these emergent abilities will appear. We don't know the level of their ability until they do appear. And then we also don't know the landscape of potential abilities that can possibly appear. Okay, so even though there are several studies with documented evidence of emerging abilities in large language models, there actually isn't a consensus about emergence in the AI community. So like I mentioned earlier, Ron and I don't actually agree on this. So are emergent abilities that have been observed in large language models signs of intelligence? Or are they just sophisticated parlor tricks or an illusion that is just created by processing massive amounts of data? So now we'll go over just several arguments for and against emergent abilities in large language models. Okay, so one of the primary examples of emergent abilities in large language models is zero-shot and few-shot learning. So the terms zero-shot and few-shot refer to the number of examples that a model is given before it's asked to perform a task. In the few-shot case, a model is given a few examples of the task in the prompt. And again, a prompt is just the text the model takes as input to determine which output it should generate. So in the example on this slide, the model is asked to translate English to French, and it's given 3 examples before it's asked to translate the word cheese to French. So this is an example of 3-shot learning. And few-shot learning shows how large language models can just rapidly adapt to new tasks with minimal input, which is a capability that mirrors the kind of flexible intelligence that is seen in humans. So now, a model is actually able to leverage its pre-existing knowledge to respond to new information based on just a few examples. So the model isn't, just recalling information, it's performing tasks in ways that it's not explicitly trained to do so. This level of natural language understanding and the generative ability that is required for something that hasn't been explicitly trained isn't something that we have observed in previous language models. But today's large language models are able to produce really, really impressive results on so many zero-shot or few-shot tasks. So where the model has just never seen the task before, or it's only been given a few examples. So now let's also look at the capacity that large language models have for logic and world knowledge. So there's these 3 statements here that show how large language models use these abilities to reason and correct inaccuracies or illogical statements. And this shows a sophisticated level of understanding that goes beyond just simple pattern recognition. So the first statement shows an understanding of geographical locations and then the logistical impossibilities that are related to travel time and distance. So just how it's just not possible to go to Australia and Miami on the same day. If you look at the second example, it shows how the model recognizes and addresses the unrealistic medical and biological statements, just like a sneeze lasting for 10 hours, through a possible understanding of human biology and common sense. And then finally, we have the last statement, which acknowledges human developmental stages and the capabilities appropriate for different stages. So understanding that infants can't actually read, let alone comprehend really complex subjects like quantum physics. So this capability to apply logical reasoning based on general word knowledge suggests an emergent property that is not present in smaller models. So now, are all of these things, these advanced capabilities that are observed in large language models signs of emergent properties? Or are they just, illusions that are shaped by ways that we measure and evaluate these models? So a team of computer scientists at Stanford University argued that these, so-called emergent abilities appear less because of some qualitative change in model behavior and more because of the way researchers are evaluating these models. So they suggest that nonlinear and discontinuous metrics might, mislead to indicate emergent abilities because they actually fail to capture the gradual linear improvements that occur as model scale. And I want to be clear, the researchers don't actually dispute the performance of large language models on any of these tasks, but just the idea that in cases where emergent abilities have been claimed, the emergence behavior actually depends on the performance metric selected.
All right. This is a pretty good example of, I think, anti-emergent behavior here. So machine learning models typically perform better, as we saw already, as the number of parameters grow. So bigger models are almost invariably better than smaller models, but that's actually not always true. There are a couple of tasks, there's actually about a dozen tasks that have been found to have what's called inverse scaling performance. That means that the models perform worse on that exact task as the number of parameters grow. And one of those is called the hindsight task. And we're looking at an example of the hindsight task here. This task checks if a language model can correctly evaluate the wisdom, the goodness of a bet by looking at the odds of the bet and the possible gains and losses and not focusing on the outcome of the bet. So in other words, if the calculated expectation of the bet is positive, then the model should recognize the bet as a good bet, no matter what the actual result of that bet turns out to be. The twist comes, obviously, is they will ask the model to assess the to assess bets where the odds were terrible, but the player still won. And this basically validates the model's decision-making ability. And if you go to the next slide, this is where it gets really, really interesting. Model performance on this hindsight task goes down. So if somebody places a really, really terrible bet with low odds and they're likely to lose money, but they won, models will actually say it was a good bet just because they won. And as the number of parameters grows, they actually believe that to be the case even more. Of course, the catch comes, if you go to the next slide, with out of the blue, we get to GPT-4, and with that parameter count, we go from declining performance to perfect performance. GPT-4 can not only get all of these hindsight neglect task questions correct, it can tell you exactly why the bet was risky or why the bet was good and speak to the statistical odds of the bet directly. So there is a lot of disagreement, I would say, within linguistic circles about large language models. Noam Chomsky wrote a critique, an op-ed piece in the New York Times last year, and he was pretty devastatingly critical of large language models. Chomsky is a towering figure within linguistics and cognitive science, so his opinion matters quite a bit. He called them, as you can see in this full quote, lumbering statistical engines for pattern matching. So he really does not respect large language models. He does not think that they are exhibiting any type of intelligence. He thinks they're just mimicking human language and have no real understanding. They in particular, he believes that they are in what he calls, quote, a pre-human cognitive phase, meaning they lack the essential capabilities for true intelligence. And he gives an example, one more example, like he says, they can't understand non-existent scenarios. So these models will believe things could be possible, even though if you really understood the world deeply and you understood physics, you would understand they were impossible. And he just thinks that they're mimicking English syntax. Scott Aaronson, who is a theoretical computer scientist at the University of Texas at Austin. He wrote a rebuttal called the False Promises of Chomskyism, and he was pretty scathing in his dismissal of Chomsky. He thinks that LLMs, despite their differences from human cognition, are actually shining a huge amount of light on our understanding of language and intelligence. And he compares the dismissal of AI's capabilities to sort of historical resistance. Yeah, good. Hold on, I should mention that Scott Aaronson will be on Hidden Layers next week. We did a great podcast together a couple of days ago, so look for that. But he compares the dismissal of large language models with sort of like Jesuit astronomers who refused to look through Galileo's telescope. He feels that it's essentially challenging our worldview, our understanding of what it means to be intelligent. And he contends that it really doesn't matter that large language models learn differently from the way humans do, that intelligence may come in all different kinds of forms. And, example would be, jets don't flap their wings to fly like birds, but they can still fly, right? So there are maybe multiple different ways to achieve, intelligence out there in the real world. Let me see. Oh, okay. I think that's the end of our presentation. So now we're going to segue over, before we do any type of question and answer, because I'm sure there are going to be some questions. We're going to just take a poll. There's not a right or wrong answer here, and Noam and I will share our perspectives here in a second, but just by a show of, I guess, hands on this, do you feel that large language models exhibit emergent behavior? Raise your hand.
Is it okay to ask for a refresher on the definition of emergent, what we're using for this question?
Yeah, I would say emergence in this context just means that there are, the way I would capture it is there are qualitative changes in behavior that appear out of the blue that are unpredictable, just given a qualitative change in the input. So meaning you reach some threshold and all of a sudden, by definition, new things appear, new capabilities appear that could not be predicted through just a simple scaling of some properties. So, okay, that is great. Okay, everybody put your hands down. Now, let's see. Raise your hand if you don't feel language models exhibit emergence behavior.
I'm abstaining. I don't know.
What's that?
I'm abstaining. I don't know.
Oh, okay, great. Okay, awesome. Okay, everybody put your hands down. All right, Numa, what do you think?
I do not think they exhibit emergent behaviors. Ron?
I think they do. And now there's not a right answer here. And I would even go so far as to say it's even fuzzy defining emergence. So this is one of the reasons this talk is so much fun. Does anybody have any questions? We got tons of questions when we gave the presentation live. So fire away if you have anything. Maybe raise your hand.
Okay. I'm going to stop sharing now so I can see people too.
Yeah, good idea. Yeah, Jupe, you're up.
Yeah, I guess question about I read an article about a paper that had come out not too long ago about emergence, and I think the paper's argument was essentially that it wasn't necessarily the emergent behaviors, it was more so how we measure these things in models.
Right.
I think that's probably why I lean more on the not emergent side. So I guess my question would be like, are there ways to measure like large language models to account or like to avoid that kind of bias essentially? Like, I don't know if that question makes sense.
No, it's a great question. You touched upon something that Numa mentioned in the presentation, which is there there is some evidence that the metric you choose to measure some property with, if that measurement has the ability or the inability to capture sort of a smooth linear representation of that underlying effect, that you could be tricked into seeing emergent behavior because you're going to see these bumps in performance. But actually, if you picked a different metric, it would be much more of a smooth curve. So you're dead on about that. Numa, what are your thoughts about the ability to find maybe metrics that would conclusively determine one way or then another that it was or wasn't?
That's a really active area of research right now, and we don't have a very standard way of measuring or evaluating large language models. So like that slide I showed, which had, a lot of different kinds of metrics. So each one, measures some aspect of large language models, and it's like a different part of evaluation. So a lot of it's nonlinear, it's discontinuous, right? So there's not like a really great way to evaluate them right now, which is also why I think we are not actually seeing a lot of the gradual linear improvements that would occur as these models scale.
That's right. Really quickly, I'm going to share my screen because this is kind of unbelievably good timing. There is this really, really great blog post by Sebastian Ritter that came out a couple days ago, and there is this crazy graph I have to show everybody. So let me set this up. This is a set of different benchmarks for different capabilities. You've got like the squad for question answering. You've got MNIST for computer vision systems ability to recognize handwritten digits. And just so this makes sense, can I make this bigger? This is normalized. You can see each of the different sort of metrics up here. This is normalized so that the original first performance level of any model in that metric is set to -1. Human level performance is 0. And then if it's above that, it's above human performance. And you can see, for example, like MNIST, this blue one, came out in the 90s, and it took until, 2014, give or take, before we had human level performance. Newer metrics like squad almost are straight vertical. Models are increasingly being able to just sort of destroy these metrics and do superhuman level performance at breakneck speeds. And so what Numa is talking about is that it's hard to come up with metrics. It's hard, and it's getting harder as these models become more capable. And so it's a really difficult problem all around. Okay, I think Michael Wharton, you had your hand up next.
Yeah, I was kind of curious, I guess, given your stance, Ron, this is a question for you, but do you have like one or two specific examples of emergent behaviors that, color your opinion more than others? And does any of that kind of boil down to subjective, like personal experience interacting with these systems, or is it more, what are like the one or two big things that swayed you?
So I didn't mention this, but I agree with this. Scott said when we were chatting last week that he said, and by the way, Scott is this like renowned quantum computing expert, and he's done really amazing work in the field of computational complexity theory. And he says the biggest scientific surprise of his entire life, and I agree with this, is that large language models can essentially pass the Turing test. That by just learning this sort of this token probability distribution on large data sets, you get what appears to be emergent intelligence. And for me, emergence is this. It's like it's when something, as we talked about earlier, if you understand all the laws governing some system, you still can't predict some behavior of the system as some aspect of that changes. So, as water gets colder, suddenly it freezes. Well, you can kind of understand that once you understand what's going on at the molecular level. But there are really complex things like, just because you understand the laws of physics, you can't predict what's going to happen in chemistry. And just because you understand the laws of chemistry, you can't understand biological systems. They're just too complex. They're almost like chaotic level complexity, which Steve Kramer can speak to in detail. And I think out of that chaos are emergent properties that are just fundamentally unpredictable. And I feel language models exhibit that, because I don't know if anybody on planet Earth expected these capabilities just by scaling up, token prediction. Numa, do you have anything to add to that? Okay. All right, Nathan, I think you're next in the queue.
Yeah, I was thinking about the question, or like the relationship between emergence and intelligence, because I think it's maybe worth going into that in a little more depth. And I almost wonder, like, emergence. It sounds like emergence is sort of more rigorously defined, although there are still a number of definitions. There's some question around it, but it feels to me like the very fundamental way that like gradient descent works on neurons is almost just in itself an example of emergence, right? You have these perceptrons that have a very simple function. You put them all together in layers, and through this backpropagation, you are coming up with more and more complex functions. And so that, I think that's I would call that a form of emergence. And then there's like varying complexity, and it's almost like a sliding scale of the complexity of the emergence. And then at some point, there's more philosophical about whether it's intelligence. But I'd be curious, Ron, Numa, or others, if people have thoughts on like the relationship between emergence and intelligence.
I have some thoughts, but Numa, you go first.
I think emergence can be a sign of intelligence. I don't think it has to be a sign of intelligence. I don't think properties have to be emergent for it to be intelligent, and vice versa. But I think emergence can potentially be a sign of intelligence.
Yeah, I think I would agree with that. And the difficult thing is we don't even agree fundamentally on what intelligence is, right? And so one of the challenges that we're facing collectively is we're in this age, we're approaching this age of AGI, and we're not really even sure what intelligence is, let alone consciousness, right? And so how we measure this, how we define this can change what we see. And so my personal belief is that if you try to introspect your thought process, when you begin to say a sentence, you don't know every word you're going to say, right? Especially if you're trying to express a really complex thought. You probably have this idea that is some point in this high dimensional latent space sticking with the neural network analog, and semantically what you want to communicate, and you're choosing your words as you communicate. And so I think our own intelligence, our own language abilities are actually closer to this language model representation than we realize. And it's only because we, again, can't introspect that. And this goes into this whole idea of illusions of consciousness that we won't really go into. But I actually think that that's one of the reasons that language models are the most important scientific discovery, because I think they're pointing to the fact that we may have fundamental misunderstandings about how our own intelligence works, just simply because we can't introspect it.
If you actually read my book and the sections for AGI and consciousness, it's just me complaining about lack of like a testable definition, or just like consensus in the scientific community. But to just slightly counter that a little bit, I think that humans are actually able to reason and understand. And while that's still a little bit hand-wavy on what it means to reason and understand, I think, like, sure, we might, pattern map similar to language models, but we're actually thinking through critical problems, and they're not. Okay.
Oh, I totally agree. And just to be clear, I don't think language models are conscious. And I don't think that they are intelligent in the same way we are. I think we have multiple subsystems of the brain, and right now language models are they sort of lack that complexity, and so I think it will put a limit on how far they can go as on that sort of intelligence stack. Stephen, you've got your hand up, please. Stephen, you're on mute.
Oh, yeah, you're right. First of all, thank you both very much. I now wish I had been able to be there at South by to see this and the crowd reaction. And I asked a question at the top of the hour whether we should do this, for webinar content, and maybe we should ask, other people what they think. My view is definitely, and I think that the context it might make sense in is to adapt it just slightly and aim it at people who have to do corporate AI governance, like boards, and explain and use it as a way to explain, you have to pay attention to this stuff because these emergent properties are going to generate risks and liabilities that you have to govern and mitigate against. And I think it would be a really compelling set of content to help them understand why this is so important for them. So
that's a really great point. I hadn't thought about it from that perspective yet. I like that idea. Ben.
Yeah, I'm curious if you think there will ever reach a point as time goes on where the answer will become clearer on whether or not they are emergent, yes or no, because it seems like there's a lot of theories supporting both sides. So I'm wondering, if that's a thing that will come with over time, or it's just going to be the same, scenario just evolving.
I think New and I would probably both agree that the answer would be yeah. We'll eventually figure out the answer to this question. Maybe even in our lifetimes. I don't know. It's just such. It's almost like a philosophical question. You know what I mean? It is so complex, and I think we're missing. We might be missing some core concepts, for lack of a better word, about how to even think about this and measure it in a way that we can all agree is more scientific. Because the challenge is, one of my favorite definitions of emergence is almost unbelievably fuzzy. A quantitative change given some qualitative vice versa. Like, well, hold on, what do you mean by qualitative? Like, baked into the definition is something that's not quantitative, right? It's like, oh, you'll know it when you see it. It's almost like the definition of profanity, right? It's like you'll know it when you see it, but it's not specifically defined.
Testable definitions are really the dream. And I do think we'll get there. I just think it'll take some time.
Totally agree. All right. Any other questions? Yeah, Edward.
Do y'all feel like there's a potential, just with society at large, to mistake? Damn, I had this question clear in my head. Now it's not. But basically, mistake the Turing test for consciousness and create ethical wars on treatment of AI.
What was that last part? What was that last thing you said?
Ethical wars about the treatment of AI systems. That's not really. I had a clear way to say it. Maybe it'll come back to me, but that's roughly what I'm trying to ask.
And this is around the idea that the Turing test and as these systems become sort of more human-like and intelligent, how we treat them, all of a sudden ethical issues will come up. Is that the area?
I guess it doesn't surprise me that a memorization engine could be hard to distinguish from a human in many situations and become increasingly like that. And I guess I'm just curious if y'all feel like that's going to be fuzzy for
Yeah, no, I that's a great question. I definitely do not know the answer to that. I think, that's kind of like uncharted territory. Numa, any thoughts there?
I actually ended up like breaking up for like a good minute there. Could you repeat the question?
Yeah, just if y'all feel any sense that things would get a little messy if a lot of humans can't tell the difference between AI and a human in many situations. Outside of like deep fakes are obviously a messy situation, but more like any other forms of
I think they're
messiness.
already kind of messy. And I think they're only getting messier. But yeah, I think we see that with like human chatbot relationships. We see a lot of that with, people thinking large language models have more capabilities than they actually do. So like even just things like, lawyers submitting briefs with non-existent cases. So like I think that's just an example of how we're starting to see that already. And I think with like, GPT-4, like, the thing that just came out, it's only getting messier.
Yeah, that makes sense. That's a good example, especially that's what I'm talking about. Cool.
All right. Well, thank you, Edward. I think that's a wrap, everybody. Yes, yeah, that's a good note to end on.
I didn't
right.
interrupt.
No problem. All right. Thanks, everybody. Appreciate your great questions.
Thanks a ton, Ron. It's easy. This
Thank
was
you.
awesome.
Great job.
That was great.
Thanks, everybody.
Bye, everybody.
Bye, y'all.